Today, she will talk about unveiling new fields beyond the standard model of cosmology with Galaxies. We are very much looking forward to your talk. Thank you very much.
Great. Can everyone hear me? Thank you. So thank you for Professor Mr. Giltis for the very comprehensive and nice introduction. So I'm really glad to be here to talk to you about how to look for new physics in the realm of cosmology and also using the galaxies. So let's begin. First, why cosmology? So cosmology presents us with some of the most fascinating questions, including what is the origin of the universe and also how it evolves. So these questions have intrigued humanity for hundreds or even thousands of years. So back a few hundred years ago, and this is the geocentric view of the universe, and at that time people think we are placed at the center of the universe. This is where we are, the Earth, and then we are surrounded by these 7 celestial spheres. But of course, this view has been although dominated for hundreds of years, but with the recent science advancement, we think universe differently. And this is how we view our universe today. So first of all, very interestingly, it is not a static universe, but rather it is dynamical. So in our current view, our universe has a beginning, and then it evolved for all the 14 billion years, and this is where we are now. So we also understand that our universe is expanding during this phase. So if now we look back in the universe, and then we, for example, see these 3-dimensional distributions of the galaxies, as well as we receive the ancient photons emitted by this flat scattering surface, the so-called cosmic microwave background. And in our current picture, there are 2 phases of the universe that are extremely interesting. One of them that is closer to us, we realize that our universe is not only expanding, but also expanding faster and faster. And then the reason to account for that is the so-called dark energy that has a very mysterious form of energy that has a negative pressure that drives the expansion of the universe, accelerated expansion of the universe. So this form of energy is pretty peculiar because it is not familiar to us. Like if you think about the usual form of energy, and if I use this cartoon to illustrate that if we have this box to then to represent the size of our universe, and if we have a fixed number of particles within this box. So as the space expands, then the energy density is going to dilute for the usual like matters or radiations like photons. But in terms of dark energy, it is somehow a property that is associated with the space itself, such that when the space expands, but its energy density just kept as constant. Our kind of a current understanding or standard understanding of the dark energy, which is a cosmological constant, is a constant both in space and also in time. Another really fascinating phase in our current understanding of the universe is way back in the beginning of the universe. So when our universe was still like a baby universe, it expanded like really fast within 10 to the minus 30 seconds. And within this short period of time, it expanded by 10 to the 30 times. So there's a wide dynamical range in this so-called inflationary stage of the universe. And also during this period of time, it stretched this initial quantum fluctuations onto the much larger scale. And this also set the initial condition of the later matter distribution, so the density and also the cosmic structure that we see later on. So maybe now you want to ask me, how do I know all these? Something happened all the way 14 billion years ago, and also some mysterious form of energy that we don't even know its nature. That is because we have this remarkable cosmological data set. So on the left-hand side, you see this as an example of the cosmic microwave background, which are basically these ancient photons propagated when the universe was still very young, which is 380,000 years ago. Oh, and these colors basically show the fluctuations of the temperature from these ancient photons. On the right-hand side, we see this is a map of the galaxy distribution, and these colors there show the density fluctuations of the galaxy field. And there we can see like these filamentary structures, but we can also see these black point or black regions that is also known as, for example, the cosmic voids. So combining these amazing, remarkable cosmological probes, now we arrive at a standard model of cosmology. And basically in this standard model that tells two things. It tells us what is the initial condition of the universe that is given by inflation. And also it tells us what is the lifetime dynamics of the universe that is given by this so-called cosmological constant denoted by this lambda, as well as the cold dark matter, which is a form of matter that barely interacts with photons, so they are invisible. And I also want to highlight that on the right-hand side in this map, what we can see from this galaxy distribution are just 5% of the total universe, whereas the majority of the energy budget of our universe is actually in an invisible form. So these data have a lot of degrees of freedom, are really abundant in the information. But one of the beauty of this cosmological model is that it allows us to compress these very complicated data. So for example, in these galaxy maps, there are typically like millions of galaxies, whereas in the CMB case, there are like also millions of pixels. But then with the standard model, basically it tells us that these systems can be compressed down to this fixed set of so-called cosmological parameters that basically tell us what is the energy budget, what is the expansion of the universe, and also how these matter they fluctuate in our universe. So this model is beautiful and also has been a tremendous success that has been proved by many data. But we still have these fundamental questions that are unresolved, namely, what is the nature of dark energy, and also what is the nature of dark matter, as well as what is the physical mechanism for the inflation. So in order to address this question and ask whether we should also go beyond this standard paradigm, and I would like to raise these two what questions. So first of all, what are the signs that will indicate there's new physics and tell us our current understanding is indeed incomplete? And the second question is, if this is really the case, then what is the cosmological probe that we should use? So let's go through these questions. So first of all, what are the signs? And here I would advocate we'll look for tension and anomaly. So what I mean by tension is when we look at the real data, for example, and we suppose these different data sets, multiple data sets, they should be given by the common underlying model. But now if we go to the experiment and measure whether these parameters agree or not, for example, this is a very famous experiment from the so-called Hubble tension, where the Hubble is a parameter associated with the cosmic expansion. And very interestingly, people have been finding for long that they're using the so-called Fermi probe, which are the probes related to like from the cosmic background, versus the Leyton probe in red and dark, coming from, for example, from a supernovae. And there has been this 4.4 sigma discrepancy. See, these data, they do not agree with each other. So this is one indication that maybe there is a bit gap in our current understanding. And another place we can look at is the so-called anomaly. And by anomaly means we again have an underlying theory, but now we go to the data and measure some features. And if there are features that are not predicted by our model, then we would call it as an anomaly. So here I want to use this plot as one example to show the search for so-called parity violation. I'm going to come back to this plot again later. But here, for the moment, I just want to draw your attention to this black histogram, which represents our current and standard understanding of how the universe should behave. Whereas this orange vertical line shows what we measured from the data. And then the disagreement between the data and also the black histogram indeed tells us there is a discrepancy in the real data. And that could be a sign indicating that there is an anomaly in the cosmological data set. So these are just two examples, and there are many more essentially in recent years with increasing tension and anomaly. I'm not going to go through all of them, but I do want to say that this sets a motivation of saying, why do we want to go beyond the current paradigm? Why do we want to look for new physics? And the next question is, okay, given that, which cosmological probe should I use? So there are many fascinating cosmological probes, and one of them I'm particularly excited about is the so-called large-scale structure. So here by large scale, I'm talking about the unit of megaparsec. So there are orders of millions of years, or like 10 to the 22 in terms of meters. So the reason why these large-scale structures are really interesting is because they encode information about the origin and also evolution of the universe. So as we mentioned before that this inflationary stage sets the initial condition of this density fluctuation of the cosmic structure. And here I'm using some simulations from the so-called Millennium Project. And basically what we see from these simulations, they indicate the cosmic web of the dark matter and also the large-scale structure it forms. And here we can see that as we go from left to right, as time increases, there is more and more of these density contrast, and that also indicates more and more structure formation. So this is essentially by looking at this large-scale structure, we have the initial condition, we have access to the initial condition, and also this late-time dynamics is basically governed by our best knowledge of gravity from the general relativity. So that's why they carry the information both about the beginning and also its evolution. But now there's also a question that we said before that we cannot see dark matter. They barely interact with photons. So how can we study something that we cannot see? So although we cannot see dark matter, but galaxies, they are bright. So we can use galaxies to trace these large-scale structure, to trace this dark matter. And here I use these zooming simulations as one example. It's a little bit blocked, but basically on the large scale, we see this large scale structure. But as we zoom in these simulations, and then we can also see that these bright spots, so they represent the galaxies. So while we cannot see this like underlying structure, but then we can use the bright galaxies to trace the structure. Say that galaxies, they serve as luminous tracers of this underlying matter field. So this is also the motivation for the galaxy surveys over the past years to map out the three-dimensional universe. Let me see if I can get rid of this bar. Okay, great. We can map out this invisible three-dimensional universe, but with the bright galaxies or the quasars. So over the past decades, there have been many galaxy surveys. But here I want to take this EVOS, the Extended Variable Acoustic Oscillation Spectroscopic Survey, as one example. So it's very interesting with this survey because it is as a benchmark survey for ground-based spectroscopic surveys as the one that is currently ongoing. And the EVOS, which maps out a sky coverage about 10,000 square degrees and has a sky coverage about 25% of the full sky. And it also traces about 1 million galaxies and quasars. So here in this diagram, we are the center, and then we look backwards in time. So within EVOS, it uses different type of galaxies to trace the underlying matter field. So here, these colored cones we see here, they represent the type of galaxies. So maybe the resolution is not enough, but essentially each of the points in these colored cones, they represent one galaxy. And then from the low redshift to the high redshift, the redshift is a quantity that measures the distance between the galaxies to us. So the low redshift means the galaxies that are closer to us, and high redshift means the galaxies that are further away. So from the low redshift, we have those so-called luminous red galaxies. They are older and elliptical galaxies. And then moving to the high redshift, there is the younger galaxies like the emission line galaxies that are also star forming. But then as we go to even higher redshift, that the galaxies are eventually become very distant, from us, and also they are becoming too faint. So for that purpose, we need to use some very bright objects, and that's the reason we use the quasars. So these quasars, they are believed to be powered by the supermassive black hole, and then through the accretion process, they produce a lot of light and also heat and make them extremely bright. So that's how we can like build this program step by step and then go from low redshift to the high redshift for the galaxy survey. So as we recall that for these modern surveys, that typically involves about millions of galaxies. But if we just want to naively report the positions of each individual galaxies, move this back. That is going to result in a data vector that with extremely high dimension, that is going to be like a million, order of a million. So now, can we like have a way to more efficiently characterize the distribution of the galaxies, as well as to compress this huge dimensional data vector? And the short answer is yes. We can use the so-called summary statistics. And the lowest order summary statistics, and also the one that is mostly widely used, is the so-called two-point statistics. So they can be used to characterize the galaxy distribution. And basically you ask, what is the probability access of finding a galaxy pair over a uniformly random distribution at a given separation distance? And basically these two-point functions, they also quantify the correlation of the density at a given scale. So doing that, on the left-hand side, you see a measurement of a two-point function applied to the real data. So here, basically, we are seeing this two-point function plotted as pair separation distance. And then these two different curves basically means we measure this pair separation along different directions with respect to the line of sight. And here in this plot, we can also see this fun feature that is associated with the baryoacoustic oscillation. So the basic idea is we see these dashed curves. So this is the model prediction. And these models, they are a function of the cosmological parameters. And the idea is that we want to tune these models such that they go through this curve in the back, or we want to fit these models. And that is how we tie the measurement of the two-point function and then with the cosmology. So on the right-hand side in this plot, it shows the constraints of our current understanding of dark energy. And basically it plots these equation of state parameters of the dark energy, and that is a parameter that denotes what is the ratio between the pressure and also the energy density. So if we are in a lambda CDM scenario that is given by this plot, then we should expect the so-called W naught that is sitting at -1 and this WA that characterize the time varying component of the dark energy to be 0. So now we look at data. The blue is the red contour is from the combining data from the cosmic microwave background and also with supernovae. And the blue is the CMB with the SDSS, and the gray is combining all the three data sets. And by the way, the different shaded region denotes the different level of confidence region. And so from the SDSS era, here we see that the gray contour agrees with the lambda CDM pretty well. There is no discrepancy there. So far so good. And but then this is what we measured back 5 years ago. So back then we could ask ourselves, do we accept the lambda CDM as an ultimate theory? Do we just stop there? Or if we still recall that the EVOS only covers about 25% of the total sky area. So can we still be limited by the statistical fluctuation? So based on this question, that exactly brings us to the next generation survey, the dark energy spectroscopic instrument. So this was a photo I took 2 weeks ago while I was in the in-person observing in Tucson. And here you can see this is this is the telescope that holds the DESI instrument. And today I also brought a 3D print I got as a souvenir when I was doing my supporting observing, and you can pass it around to take a look. So the DESI, coming back to DESI, so DESI is it's a ground-based telescope located in the Cape Peak in Tucson. And it is also a so-called fiber-fed system. So what I mean by the fiber-fed mainly means it uses fibers to collect the light from the galaxies. And here we can see this cool animation of the fiber rompers that host these fibers, and they are plugged into this focal plane. So, so far, DESI, although it is just released its first year data, but it already collected 4.7 million galaxies and also quasars. So this has been the largest data set we have so far. And currently, I'm also leading working group within the DESI for the next data release. So one of the most intriguing story or result found by DESI year one is if we come back to this plot again, the constraints of the dark energy. So if we recall that for the lambda CDM, we should find the result to be fit on this black plot. But then with this new data set, we actually found they do not agree with each other. Given by this new control, there's like a 2 or 3 sigma discrepancy with this new data. So this is very interesting because this may be a hint and say that perhaps the dark energy is not as what you think as a cosmological constant, but rather has a time-dependent component goes into it. So beyond the ground-based telescope, there's also this very exciting program that is launched very soon by the end of 2026, the Nancy Grace Roman Space Telescope. So being in space, it can be free, for example, from the Earth atmosphere, and that allows us going to even higher redshift. So indeed, with Roman, the survey is going to the redshift up to 3 and also collect about 12 million galaxy spectra. And currently, I am a collaborator on a funded Roman team. So given these unprecedented data sets, how can we extract most information from these data sets? So what I mean by information is something that we don't know. So what we know is our universe, the density fluctuation in our universe is very close to a Gaussian distribution, just given by central limit theorem. What we don't know is how much it actually deviates from the Gaussian distribution. And we do expect that to happen because the way time, the nonlinear gravitational evolution, they introduce this nonlinearity and also introduce this non-Gaussianity. And also, if the initial condition deviates from a standard inflationary scenario, and we also expect there is non-Gaussianity already implanted in the initial scene. So if our universe had been a pure Gaussian universe, then the 2-point function, the pair count already captures all the information. So that's essentially why the major surveys so far have been just going for the pair counts. But we also now know that they do not capture all the information. So in order to do so, we need to go beyond the pair counts. So what do we mean by pair count? So conceptually, it's very easy to understand. So this is our pair count. We take 2 galaxies. And what we also can do is we can look galaxy triangles, the triplets, or formerly known as the 3-point function. Or we could also look at galaxy particles, 4 galaxies, or known as the 4-point function. Well, this is conceptually easy to do, but putting in practical form, especially when we look at computational speed, this is almost prohibitive. It grows combinatorially. Say this scheme goes as the number of galaxies to the nth power. And for example, if you want to do 3-point function, this will easily result in 10 to the 18 number of triplets or 10 to the 24 number of particles. So even if we put this onto the state-of-the-art GPUs, that would take years to centuries for us to finish this calculation. So the question is, in the next, how can we speed up these algorithms? So broadly speaking, I will characterize them into 2 types. One is based on the so-called compressive statistics, and the other one is use a harmonic-based statistics. And the next, I'm going to briefly introduce what are these algorithms. So come to the first, the compressed statistic. And the basic idea here is let's take pair of the galaxies or density fields and then weigh them such that they form a composite field. So from outside, just look like a single galaxy. And then we let them cross-correlate with another single bare field, such that they form like a pairwise calculation. So this scheme is very nice because by doing so from outside, it just looks like a pair counting. But inside, we know that we took 3 density fields and it encodes information about 3 fields. And it also becomes much faster and also has the advantage that it reduces the dimensionality of the data vector. So given this very promising scheme, my collaborator and I, we also run some simulation to access what is the actual potential of this new statistic in extracting the cosmological information. So here in this triangle plot, basically I'm showing the different combinations of the cosmological parameters. But let me take this zoom in panel as one example. So here I'm plotting the so-called sigma 8 that denotes the structure fluctuation and versus the omega measure, which is the matter density. And these different ellipses basically show the arrow bar. So the smaller the ellipsis, that means the arrow bar, like the better. And the gray contour here is from the so-called power spectrum. It is a pair correlation. And the red one is from the so-called skew spectra, which is from the new scheme. And the green one is combining the power spectrum and also the skew spectra. So from this estimation, from the so-called forecast, what we learned is, in principle, this new scheme can improve relative to the older or the pairwise calculation by a factor of 2 or 30%. So this looks very promising in principle, but the next question is, we are really interested in extracting going from the left to right. We want to measure the skew spectra from the data, but then infer the cosmological parameters. So how can we do that? So in the traditional approach, there are a few ingredients, such as we need to model the skew spectra. We need to estimate its arrow bar, and we also need to come up with an likelihood. But each of these steps are actually pretty challenged if we want to derive these, specifically if we want to derive a model analytically. So because of this challenge, one approach with my collaborators we explore is to use a machine learning-based approach to directly learn the parameter distribution. So this is a program I did with the simulation-based inference of Galaxies and the team member. So with this machine learning-based approach, we could bypass these traditional difficulties in the modeling, in the likelihood, as well as in the covariance matrix. And the basic scheme is that we take 20,000 of the synthetic galaxy catalog from the simulation. And there, because we run the simulation, we also know what is the wrong truth of cosmology. And from there, we measure the galaxy skew spectra, and we put that as a joint distribution into the neural network. And basically, let this neural network learn the mapping between the measurement and also the raw truth. So from there, we get a model for the density estimator, denoted by this Q-phi. And in the next step, we use the real data. So these are the real data we take from the telescope. And from there, we measure the galaxy skew spectra. And input this model, we can get to the cosmological parameter distribution. So this is the result we get. And again, I'm plotting different combinations of the cosmological parameters. And the gray contour denotes the result we infer from the pairwise or from the power spectrum. And the blue is from the skew spectra, and the red is from another scheme for the high order statistics using the free field information. And the takeaway message here is for the high order statistics, we can see an improvement up to 30% relative to the 2-point functions. So here I want to emphasize that this 30% is actually pretty substantial, because if we think that the arrow bar scales as the square root of the volume, a 30% improvement almost corresponds to an increase in the volume by 60%. So this has been like a really promising research, but we're not stopping there, because we have still a second question to answer about the anomaly. So here, I want to use the example of violation of the parity symmetry as one example to illustrate how can we search for anomaly in cosmological data. So what I mean by parity transformation is basically the spatial inversion. And I guess many condensed matter physicists here are very familiar with this idea that we go from the positive x, y, z coordinate to the minus x, y, z coordinate. So if I use this cartoon to illustrate this idea, say if I have this spinning ball and emit light from the top. So outside of the mirror, I can apply the right-hand rule to describe the system. But now if I do a parity transformation and also put the spinning ball into the mirror, then this rotation, the spinning direction of the spinning ball gets flipped, while this direction of the spinning ball that emits light still keep the same. But then because of that, I need to use the left-hand rule to describe the system. So why the parity symmetry matters? Because it could be associated with this barogenesis, which basically says why we have this matter and antimatter asymmetry in the universe. So back in the 1967, Sakharov proposed this series of conditions, and one of them is saying that we need to have the C and also the CP violation in order to explain the barogenesis, where the P here stands for parity and C is for the charge conjugation. For example, if we think about a pair of the electron and the positron pair, they have the same mass, but they have opposite charge. So if now we also want to ask whether the parity symmetry is a ubiquitous idea in nature, actually not. If we plot all these different events on different scales, like for us on kinetic scales, or for molecular atoms, or for example, for the amino acid, we see many examples that they do break the parity symmetry. However, if we go to the much smaller scales, the scales that they are so small that we cannot see what is exactly going on, or if we go to the much larger scales, they are so large such that we cannot comprehend everything all at once. Then the most natural assumption goes in there is to assume there is symmetry. There is rotational symmetry, translational symmetry, and also including a parity symmetry. But then we go to the experiment and then measure whether this assumption holds or not. For example, this was the case back in the 1956 with the neutrino experiment that there by Van Wu, and there they measured the isotope decay and found out that, okay, actually in the weak interaction, the parity symmetry is actually broken. So that was such a big surprise and also led to a new chapter in particle physics. So now we also want to ask this question on cosmological scale and ask whether we should also make this natural assumption there or not. And another really interesting perspective about parity violation is, at the beginning, I was mentioning that the inflation sets up the initial condition of these primordial density fluctuation. And then through evolution, it can leave imprints on the density distribution. So now if there is also a mechanism that is beyond the standard inflationary model, then that is also parity violating, that can be picked out by the density distribution. For example, here is a slide of simulation run by me and my collaborator. And here you can see these really interesting helical structures that is not present if we just run a standard simulation. So now the question is, how can we pick out these really interesting structures using galaxies? So I can give a spoiler. The answer is we need to use at least 4 galaxies. And why is that? So let me also use this cartoon to illustrate this idea. That here I use this galaxy quartet and let each of the vertex represent one galaxy. And I also range such that the neighboring galaxies with respect to this closer one, I call it primary galaxy, to be the R1, R2, and also R3. I also range such that the 1 is smaller than 2 than 3. So now if I apply a parity transformation of this quartet, so before if I look from top to down, I'll see that the arrangement goes like clockwise. But now if I do a parity transformation, it's the handedness at this vertex is going to flip. So if we had replaced this exercise with a line, like with a pair count or with a triangle with a 3 points, and we can still do the Perry transformation, but then the thing is we can always rotate such that this line or triangle is going to overlap with its original image. But this is not going to happen for the galaxy quartet. We can do this exercise afterwards, but I hope I can convince you that you will not be able to rotate your left and the right hand into each other. So that is basically saying that we need to have at least 4 points in order to cope with parity symmetry. However, there we encounter again the old problem about the computational speed. So this time we use a different scheme that is based on a harmonic decomposition. So basically the idea is on the left-hand side, this is our 4-point function. And we decompose it into a radial-dependent piece and also an angular-dependent piece. So by doing so, this angular-dependent piece has a lot of nice properties. For example, it allows us to factorize the quartet counts. So before we need to find all these 4 galaxies all at once, but then because of this angular basis, we can factorize this quartet counting into this pairwise counting. So that allows us to reduce a lot of the computational complexity. And furthermore, over the years, we also accelerated this algorithm using the GPUs. And just one takeaway is we don't need to wait for centuries to finish a calculation, but literally we can just do it within a minute. So that's much faster. And another really nice property associated with this angular basis is, I'm not going to show the math behind, but I can tell you that after you do all these simplifications and especially write these angular bases in a Cartesian representation, there is this very familiar structure, the scalar product. So basically the scalar product is again telling us we have this tangentness. So now if we do a parity transformation of the scalar product, we're going to see this minus sign then in front of the spaces. So that is like the trick, how we can pick out the parity information from the 4-point function with this algorithm. So now that we have a fast algorithm, we have an algorithm that is also sensitive to the parity transformation. What are we going to do next? We're going to apply it to the real data. So this is one of the very interesting measurements we find with this scheme and applied to the real data from BOSS. So here, I've seen this plot before already, but I would like to guide your eye again to this black histogram. So this black histogram are run with simulation without parity violating mechanism. And that basically tells us if our universe has nothing new happens, where we should expect the center of the distribution as well as where we should expect the center of the distribution. And this orange vertical line is when we measure from the real data. And here we can clearly see that there is a discrepancy, and actually a discrepancy at a 7 sigma level. So in this BOSS survey, there are 2 subsamples. One is a larger sample, and there we measured with 7 sigma, and another smaller subsample we measured with a 3 sigma. So just from the number wise, it makes sense because the larger sample has a smaller error bar, and that gives a higher detector significance. So this work has triggered a lot of, including seminars or workshops, and also a series of theory papers, as well as machine learning papers, and also even papers that redid our analysis completely. So right now we understand that there are still outstanding questions that we need to further push to understand, including understanding the systematics in the data analysis. That is always one of the central questions, as well as to what precision level can we understand the error bar. That is a question about the error bar, how well we can understand that. So that's why it is very interesting to have more follow-up study from different angles, both into the data analysis, into the model building, as well as into developing new algorithms that can provide us a different angle in looking for this problem. So with that, I would like to spend a few minutes on where I would like to go in the next. So for my future research at Missouri, so on the one hand, I have this core question about understanding the origin and evolution of the universe. And then I see my research has these 3 pillars in terms of the algorithm and also data and also the theory. So coming to the algorithm side, on the one hand, I would like to push more development in efficient estimators, as well as explore different regions, like using the machine learning based approach, using simulation based inference. And on the theory side, overall, I am excited about making this bridging between the underlying theory as well as the observables. And on the data side, I'm excited about exploring larger and also independent data sets, as well as understanding more about the systematics. How much time do I have left? Okay. So to give some example about the student projects and also about the development in the direction of the algorithms. So over the past years, I've been very lucky and then advised these undergraduate students. For example, both Ronan and also James came to us as the RU summer students. And within just 3 months of summer program, and they made really good progress, and then led to conference presentation. And especially for James, he worked with us for an additional year, and that also led to his first publication. And moreover, both Ronan and also James, they are admitted by Princeton from last year. And then from James' work, that also triggered another bachelor research with Victoria, that she applied the code developed by James and to study from the magneto hydrodynamic simulations. And then coming to the theory side, and here are again some examples about the student projects. And here, for example, with William and also with Matthew. And they are both PhD students at University of Florida. And now we try to understand how to make the connection between the theory and also the galaxy observables. Both try to connect from the nonlinear evaluation of the galaxies, as well as how do we connect from these inflationary theory calculations. And finally, while in my talk I've been focused on the galaxies, the surveys for the Dead Sea and also for Roman. But essentially, if we look at this bigger landscape, there are many more surveys that are upcoming. So in this plot where I show the number density as well as the survey area. So for the future surveys, they are all going to the higher and upper column. Is there a question? Yeah. So so in the future, we're going to have many more exciting galaxy surveys. And with that, with my collaborators, we also made forecasts and to see what are the opportunities from these upcoming surveys. And broadly speaking, they can teach us a lot more in terms of like target violation or the non-standard inflationary scenarios, and also more into the structural growth. And with that, I would like to drive it to my conclusion. So on the one hand, I hope I convince you that the galaxies, they encode a lot of information about the origin and also evolution of the universe. And then I'm very excited about developing various novel algorithms and to probe tensions, anomalies, and also to uncover new physics. And finally, with the upcoming surveys, they will offer unprecedented precision on the clustering measurement. And we'll hope to make a lot of new discoveries. And with that, I would like to thank you for your attention.
Thank you, Jiamin, for this great talk. So let's start with questions first from the students, maybe.
I have a simple question. So when you're looking at the large scale structures, you're using the galaxies to mark the position. So what's the basis of the assumption that the dark matter also follows the same structure?
So the structure formation is like we have kind of these let us say it as a bottom-up approach that we have this natural say fluctuation, and this initial condition was set by inflation. And then we form the dark matter, and this dark matter, they grow under the gravitational evolution. And then as it grows and collects and so on, and then within this density field, gradually you form the galaxies, and then also the stars, and also the observable objects. So in that approach, you will see that these galaxies, they will naturally form where you have the overdensity field from dark matter. And that's why we can use the galaxy to trace this underlying matter field.
I have a question when you mentioned the computing the three-point function. You might mention it, but I missed it. So for the triplets, you said they're around 10 to 18. And for popcorn, it might be even more than that. So it's impossible to compute with the field. How did you compute? Because you show some results with the three-point function. Do you compute the sum and the network or?
Right. So the number that I gave was to assume that if we just do this brute force counting, then we say that if we really take 3 galaxies all at once, and we have different ways to accelerate this calculation, and one of them is using this compressed statistic. And basically, it treats 2 galaxies effectively as a 2 density field, effectively as 1 density field. And then you cross-correlate with a 3rd density field, such that from the outside, it still looks like a pairwise calculation. And this is one thing that becomes the attraction. And another one is the second part. I talk about the harmonic algorithm, that you sit on one galaxy, and then basically you decompose the Fourier function into the angular basis. Let me see if I can have backup slides to explain this. It's a little bit hard to see which slide is it. Sorry about the scrolling. Really not see it at the moment, but the basic idea is that this angular base itself, it is formed of spherical harmonics. It is formed of the product of spherical harmonics. And then, because of this factorizability of the spherical harmonics, we can decompose the angular separation of the galaxies into the pairwise counting, such that from outside, from operational wise, we just need to calculate galaxy pair, and then we get the coefficient that are associated with this given pair, and then accumulate it back to this primary galaxy, and then essentially loop over all the galaxies in the survey in the simulation catalog, such that the complexity instead of the 4-point function, but it's rather like a pair calculation.
If I understand correctly, the 3-point function is calculated based on a pair of the 2-point function.
In the example I gave is, but essentially you could also apply this harmonic decomposition to the 3-point, as well as you could also apply this compressed idea of, say, pairing the galaxy and then form like a effective 2-point calculation using a 4-point. So this is actually another really interesting program that we explored over the past years.
Yeah, you also mentioned that one student wrote calculate Python code to compute this code using the method you just mentioned.
Yes.
Okay, I will try. Thank you.
Sure. Thank you. Yes.
So you mentioned the effect of like parity violation, and how your data suggests that it very strongly suggests based on my graph that there is parity violation. What does that mean for like galaxy formation or like the effect of early information? What is the difference between parity violation and not having parity
So the scale, first of all, that we look at for the parity violation is at about 20 to 160 megaparsec per page. So this is really on a very large scale that is not yet down to like single galaxies. And then what is the implication, for example, in terms of the structure formation and so on. So if this is turned out to be true, then one of the most leading scenario is there's something really happen, something really interesting happen during the inflationary stage of the universe. And that is like, and one of the leading, for example, possibility is so-called axial inflation. So axial is basically this hypothetical particle that used to be introduced by particle physics for explaining the strong shaping problem. But then this, in the so-called axial inflation, and because axial is a pseudo-scalar field. So now if you introduce some interesting dynamic of axial with the so-called U1 gauge field, you can think about some electromagnetic field. And they can lead to some parity odd trispectrum such that that also imprints on the matter distribution on the galaxy. So if this is the case, then you can think about a whole interesting scenario that depending on the model itself, that could possibly be seen from the galaxy, but that could also be seen from other cosmological probes. So that would be like really interesting to explore, like say the joint possibilities by combining different data sets together. So in the long future.
Other questions, please?
So during this talk, at some point, you suggested that a possible reason for the discrepancy between what the standard model predicts and one of the measurements that you had might be that the cosmological constant is not a constant. Do people also think about space dependencies? Could it be inhomogeneous or in fluctuating field?
Yeah, that is a really interesting question. So there is indeed some proposals also goes into and say whether you can have this spatial inhomogeneity, for example, even to explain the dark energy itself as a whole. So my current understanding is this idea was almost proposed like 20 years ago, and so far people have been running simulations and to prove whether you can have this this explanation at all. So there have been several groups, and then running the simulation themselves could be challenging because that could eventually reduce to a question of like the resolution and also how you set up these simulations by themselves. But just zooming out, like for example, there's also the idea and say whether it could be because we are living in a big cosmic void, such that from what we observe, things that are just shifting away from us so fast. And I think those scenarios has already been ruled out. And if you really want to purely explain that dark energy from those inhomogeneity by breaking the cosmological principle, which says there is a homogeneity and also isotropy in the universe, you probably need to have much more fluctuation in the matter distribution than what we see nowadays.
Other questions, please?
I have a question. So maybe what I'm saying makes no sense, but so for the fair count, you can take the 3D correlation function, you can project it on the sphere and get the 2D correlation function, and then you expand the spherical harmonics and you get the two-dimensional correlation function. If you go to the 3-point or the 4-point correlation function, is there a simple relation between the 3D correlation function and then the two-dimensional projected in the sphere? And how can you expand? Do you still expand in spherical harmonics, or you have?
Yeah, that's so. I guess this question has maybe twofold. One is like in a physical understanding, and the other one is from algorithms, say operation. So just from building the estimator point of view, we can totally do this decomposition of an harmonic space. But the tricky part is how do we understand this connection between a quantity that you constructed on 2D, and then does that necessarily imply the quantity in 3D? So this is the question we are still currently under in understanding. Say, for example, if I take a 2D slice of some simulation, and there I measure, there's a hint about, for example, parity odd from the 2D. To what extent can I say there is a 3D parity valuing mechanism happening there? So this math is not exactly what you want clear.
Yeah. Okay. Yes. Thank you.
Did I?
Yes,
understand
yeah. You did. I was wondering, if you have, for example, effects of parity violations, how you could see the, on a slice, for example, a fixed distance, right?
Right.
Yeah.
Yes, yeah, we can talk a lot more about it.
Yes.
Like, there's a lot of interesting understanding in how this, for example, the so-called flat sky limit that matters. So basically, flat sky limit says if we take a slice that, suppose when we see our universe has a curve, has a curvature. But what happens if I just assume all these objects are super far away from us, such that we can just approximate them to live on a 2D plane? And how much does this approximation affect our real observation? And there's also this natural question, say if I see some the parity odd object, parity violation on 2D, and what is the chance that we can do this reconstruction back in 3D? Yeah, I love to talk about this much more.
Thank you.
Yes, so
Yeah, in terms of the SDI, simulation based inference, we all know that even at the level 2 point, we need a lot of simulations.
Yeah.
And you try to include more high order statistics, which basically blows up the dimension of the data vector, right? So what is your opinion about, how many realizations we need, how accurate they should be?
Yeah, so that is also a very good point. But what we actually learned really interesting from this project was the dimensionality of the data vector itself seemed to play less of a role compared to the absolute size of the simulation. For example, in terms of the bispectrum, and there we have a data vector of like a few thousand or even 10,000. So before we run, we indeed worry about this problem that, okay, this data vector is much larger than the power spectrum. Is it going to give us worse constraint? But in the end, it turns out it was not. Because somehow, even you are living in this very large dimensionality for the bispectrum, but this additional information from the bispectrum allow us to pick out some hyperparameter space in terms of this neural network much better compared to using a power spectrum. So in the end, the training for the bispectrum was even simpler compared to the power spectrum as well. But regarding the limited number of simulation, that is indeed a very good question. And that's the reason why we are also thinking about using faster simulations and also like cheaper simulation rather than using a full rigorous calculation, so-called envelope simulation, to speed up this training process.
I have a general question. The approach that you described was involved training machine learning on the synthetic data and then applying to experimental data. Isn't there a bias introduced by if you train on synthetic data? How can you get anything new from applying it to experimental data because it already has the bias?
So the idea here is using this training data set. Okay, there is an underlying assumption by assuming that our universe is lambda CDM. So it is saying that we assume it is lambda CDM, but then, of course, if there is a deviation, we're going to see it. But the idea of using this lambda CDM-based training data is to understand what is this mapping between if I know what is the ground truth and what I observe, and this relation is almost like a response and say, if I have a more fluctuation in the universe, how is it going to reflect in my observables such as power spectrum or pair count or triplet counting. So once it learns this relation, and that is the part we put into the real data and say, okay, for the real data, now this is what I measure and tell me how the universe had reacted or how had behaved such that it produced this observable. If that makes sense.
other questions here? Okay, if this is the case, let's thank our speaker.